Today we're going to be talking about exponential functions. Before we can start talking about what an exponential function is and what it looks like and some of the characteristics that it has, you do need to know this key term. So we are going to be talking about something called an asymptote today. So an asymptote is a line that a curve approaches but never reaches. I will be drawing them in with a dotted line just so that you can visually see where they are. But as long as you know that the graph will never actually touch that line or cross that line, you're going to understand the lesson a little bit better. When talking about exponential functions, it's important to talk about what the function looks like. So an exponential function looks like f of x is equal to b to the power of x, or we could rewrite it as y is equal to b to the power of x. Now, moving on, you can see in the graph below and in the information given here, our domain is XER. So basically, we can have any single x value possible when we're talking about exponential functions. Our range is YER such that y is greater than 0. So all of our function will be above the 0 in the y-axis. So everything will be positive. Notice it also does not say equal to 0. It is strictly greater than 0. Now, I mentioned earlier that there is something called an asymptote. On this graph and in your exponential functions, without any transformations, the asymptote will always be at the x-axis. So no matter what, these graphs will get closer and closer and closer, but they will never actually touch. So you'll see that I mentioned that here, the function has a horizontal asymptote at the x-axis. The next thing that I am going to be talking about is the actual function itself and how that changes what the graph looks like. So we have two graphs here. Our first graph would be the red graph. This is the graph that starts at the left and slowly goes up to the right. Now, this graph is b to the x, where b is greater than 1. So if we had 2 to the x, or 7 to the x, or 10 to the x, all of those would be starting on the left and ending top right. Now, I do mention here, the bigger the number, the faster the growth. So basically, the higher the number, the steeper the line will be. In blue, we have the opposite graph. It starts high on the left and slowly decreases down to the right. Now, this is when our b would be between 0 and 1. So any kind of fraction, not an improper fraction, but any kind of regular fraction would give you this decreasing graph, and the lesser the value, the faster the decay. So this one's a little bit backwards. So if we had 1/2 and we were comparing to 1/4, the graph where the b was 1/4 would be faster decay. The last thing that I want to talk to you about is the y-intercept. So both of these graphs have the same y-intercept, and that y-intercept is 1. Now this comes from the rule where anything to the power of 0 is 1. So it only makes sense that if we plug a 0 in for our x in our y equals b to the x, we would get a value of 1 regardless of what that b was. Linear, quadratic, and exponential functions have unique difference patterns that allow them to be recognized. When looking at a linear function, we remember that they have a constant first difference. So here I have a graph for you. You could see that it's a straight line. Here I have our table of values, and if we were to calculate the first difference, we would simply take this number, subtract the number above. So -1 take away -2. And we would continue. 0 take away -1. 1 take away 0, and 2 take away 1. Since these were all the same, we know that it's linear. Quadratic functions have a constant second difference. So you could recognize a function in a graph because it's the parabola shape. In our table of values, what we're noticing when we do the first differences is that they will not be the same. So 1 take away 4. 0 take away 1, 1 take away 0, and 4 take away 1. Next, when we do the second differences in the same manner, so -1 take away -3, 1 take away negative 1 and 3 take away 1, we notice that they are the same, which means that based on this table of values, we could say that it was quadratic. Exponential functions have first differences that are related by a multiplication pattern. So the graph again is pretty obvious. It will have an asymptote, it will never cross that asymptote, and the other side will be drastically increasing or decreasing depending on the function. And when we calculate our first differences, what you're going to notice is that we're not going to get the same number. I can already see that there's no pattern here. But if I suspect that it's exponential, what I could do is divide instead of subtract. So if I have a 4 divided by 8, I would get 1/2. 2 divided by 4, 1/2. 1 divided by 2, 1/2 divided by 1, and 1/4 divided by 1/2. Since all of these are a half, when I divide, I know that it is exponential.